All right, so I guess there's only 3 people connected to Skype. So I will start. So today we will talk about renormalization conditions and the renormalization group. So in the previous lecture we've seen that we have infinities that we can remove by renormalization, meaning that we can hide these infinities into the parameters of the theory, and we can write down a renormalized Lagrangian, that is the original one plus some counter terms, and this numerically is the same as the bare Lagrangian, which is written like the classical Lagrangian, but with infinite parameters. So we have seen then that formally these bare parameters, which are infinite, depend on the original parameter, the new quantum mass parameter, mu, and in the case of dimensional regularization, also the parameter epsilon. And similarly, we have m0 is m0 of m. Now, this also depends on lambda, on the coupling, and 0. Everything depends on the coupling because this is order by order in perturbation theory. And z, the wave function renormalization, depends on, again, on lambda, the parameter defining perturbation theory, and on epsilon. Now we can think of this in 2 ways. We can think of this in the fact that, sorry, here z0. We can think that these objects, the bare quantities, are fixed. In which case, from this one, we find that the coupling constant depends on the scale mu, and then from this one we find that m, depending also on lambda, which depends on mu, then also depends on the scale mu. Remember, mu is the arbitrary quantum scale. And the same way, z is z of lambda of mu, that is to say, also depends on mu. So that's one way of thinking about it.
Professor?
Yeah?
Excuse me. Cassiano is also online waiting for your approval.
Who is it?
He sent me a message, Cassiano.
Oh, I thought you had added. I don't know why he was.
Right, I will turn off my mic a bit.
Jesus, where is this? All right, I'll just stop this because I don't see him anywhere. Oh, okay. I still don't see him, but all right. All right. So as I was saying, so this is one way of thinking about it, that these objects are fixed, and then you find that things depend through the coupling constant on the quantum parameter mu. And the other viewpoint is that you fix lambda and mu, and then you obtain that lambda 0, m0, and z are functions of the dimensional regularization parameter epsilon. And this point of view will lead to the renormalization group that we'll describe. All right. So let's talk about endpoint functions. So endpoint functions are things that depend on momenta. Depend also on the parameters m, lambda, and on the quantum objects, the scale mu, and the regularization object epsilon. But now we want to relate this to the bare endpoint function. So we want to relate to the same thing but depending on the bare parameters lambda 0 and m0, and also on epsilon. And because this is infinite. And then the relation we'll see that is with z to the power minus n over 2. So the endpoint function is related to the action. More precisely, the renormalized Lagrangian with a source, so minus j dot phi, and this is part of the partition function z, and from it we relate to w, and as you remember, then Gm is minus delta nw delta j1 delta jm. All right. So this extra term here that we add, j5, should also be invariant, meaning the renormalized function should also be equal to the bare one. And since we have that phi 0 is related to phi through z, by square root, it follows that J0 is Z phi minus 1/2 J. And then, because of this relation also, the same will be true if I put, if I put a D, a differential, and then the path ordered, so the measure, the path ordered, the measure, the d phi, is the product of all of these d phi's at the point x, meaning that there is an object C, CZ, that is the product of all of this Z phi to minus 1/2 of all possible x's. And this is what relates Z with Z0. So Z times CZ is Z0. And then, as usual, E minus W is Z. And because of this relation, then we find that W of J is W of W0 of J0 plus log CZ. Then the endpoint function, as we said, is minus dn w over z j1 del jn. Now relating with this, the dn w0 plus log cz, and then Jn with J0 as written there. So del J0 del 1 del J0n. And then the factor Z phi from the J's becomes to the power minus n over 2. And well, this thing doesn't depend on the J's, and the resulting object is J0n. So that is the original relation that we wrote. Gn n is minus z phi minus n phi. It's z phi minus n over 2 G0n with the appropriate dependencies. Then the really interesting stuff comes from not from the endpoint functions, the off-shell endpoint functions, but rather for the things related to the S matrix, meaning for the 1pi objects related to the effective action gamma. Then so the effective action gamma depends on a classical field, and as you remember, is the Legendre transformation of W. W of Z plus J phi. And then we can also write the same thing for the bare objects. Meaning, as usual, that the classical field is the derivative of W with respect to J, with a minus in front. And so and then also for the same for the bare one. All right. W is an index exponent, so it doesn't depend on anything. But J transforms from J to J0, sorry. So we obtain then also that phi 0 classical is Z phi to 1/2 phi classical. Well, so the difference between W and W0 was only in this log, oh, not Z here, sorry, CZ. In this log CZ. So the difference between gammas when I take the Legendre transformation, the only difference is this term, which is identical. This is equal to this. So then we also obtain, let me write it here. We also obtain that gamma 0 of phi 0 classical is gamma of phi classical minus log CZ.
Professor, sorry for interrupting again, but Vinicius and João Pedro are also waiting for your acceptance. And Vinicius also sent me some message, but then he stopped sending a message. I don't know if he sent you some message or not.
Let's see if I.
Vinicius Bernardes and João Pedro. They are sending me a message.
How do I?
Yeah, apparently Vinicius also sent you a message.
I'm not sure how to get there. Oh, all right. don't understand. I just cannot add them. They're not here. Well, I added them, but I don't find them when I need to add them, so that is okay, so all right, I see Ulysses you added, but I don't see him in my when I need to add them. So there's something wrong with this. Sorry, there's something wrong with this thing. So I added them to my contacts, but if you can add them, please do it because I just don't seem to find them. I just open add contacts and they're not there, even though I added them. So all right. Hopefully next time will work better than this. But so I was saying that we relate the effective action as well, and then of course we can define the endpoint functions, the 1PI endpoint functions, in a similar way. So we write that gamma n is by definition dn gamma d phi 0 1 classical d phi n classical, and so correspondingly we find gamma n of P1 Pn m lambda mu epsilon as z phi n over 2 gamma 0 n p1 pn m0 lambda 0 epsilon. So this was the physical relation that I wanted initially. Alright, so the observation that I can make here, first of all of these renormalizations were multiplicative. That is to say, none of them involved adding stuff. Everything was multiplied. So all the infinite factors were multiplied. The other observation is that, as we said, the implication is that there's a lambda of mu, and then everything depends on this lambda, which is the perturbation parameters. So everything is said to run with a scale. Meaning that there is dependence on this arbitrary scale. Now, this is an arbitrary scale, but we'll see after that you can relate to something a little bit more physical. Another comment that one can make is the bare quantities m0 and lambda 0 and phi 0 were defined usually in the UV. That is to say, the theory, the fundamental theory, is thought to be defined in the UV. Now, this is a little bit unclear because theories that we know how to deal with this renormalization idea are things like QCD, or more precisely Yang-Mills theories, in which we know that the infrared, large distances, things that we actually measure, are very messy and at large coupling, whereas in the UV at very small distances they are clearly defined. However, the thing that we mostly the thing that we have tested best is QED, which has the absolute opposite idea. It's defined in the IR, meaning for it the coupling grows with the scale, with the energy scale, and there is for this reason, and we'll see more precisely why, there is the question of whether QED makes sense in this precise formulation of quantum field theory. We'll get to that later. We'll describe this in more detail. Now, so now we said that we have to regularize and then renormalize in a certain way, and then we've found that there is a dependence on a scale. Now, in principle, there are two ways to think about this fact. One is to define what are known as subtraction schemes. That is to say, there's something divergent. We subtract the divergent part, but there's an issue that, well, since we subtract something infinite, we might as well subtract also something finite. So what do we subtract exactly? Just the infinity or something a little bit different? So that this subtraction, that scheme that I have described in the previous lecture, was called the minimal one. So this is usually defined in shorthand as MS. However, there's a variation which is the most common, that is called MS bar, minimal subtraction bar, in which we subtract the infinity, the 1 over epsilon parts. But remember that we found in all of the calculations, we found this object, psi of n. Psi, remember, is the derivative of the Euler gamma function, and the plus log of this, 4 pi mu squared over m squared. So this, on the other hand, is minus the Euler constant gamma plus stuff, and so minimal subtraction bar is also subtracting this and the 4 pi from this log. So this is subtracting this minus gamma plus log 4 pi. So you subtract the infinity and minus gamma plus log 4 pi. That's called MS bar. So that's one way to think about the renormalization. But another way is relating to this to what I wrote in here. So the fact that things depend on a mass scale. Things run with a mass scale. So, from this point of view, we define what are known as normalization conditions. So this is a more physical point of view. Remember that, for instance, the 2-point function, the term in the effective action with two fields at tree level is just p squared plus m squared. The inverse propagator. And also the 4 point at the tree level was just the coupling. So we can now imagine that things are defined. So the one PI diagrams, that is to say the effective action, is defined at some specific value of the momentum, P. Let's say P equal to 0. That's one choice. And at P equal to 0, the full thing takes the value at the tree level. That is to say, gamma 2 at P equal to 0 is what? Well, if I put P equal to 0, it's just m squared. And then also, derivative with respect to V squared of this thing is 1, right? At P equal to 0. Because I take the derivative with respect to P squared of this, I get 1. And then also from here, that gamma 4 at P squared, well, all of the P's equal to 0 is 0. All of the P's, because this one depends on only one P, but gamma 4 depends on several, or 3, 4 with a constraint. And P equal to 0 is nothing special, so I can define this at some P equal to well, P squared equal to mu bar squared. That's another possibility. So P squared now is some scale. So then I say that gamma squared at mu bar squared, P squared equal to. So gamma 2 at P squared equal to mu bar squared is the tree level. This at tree level, that is to say mu bar squared plus m squared. And then also dd P squared of gamma 2 at P squared equal to mu bar squared is also 1, and gamma 4 of pi. And here a usual definition is pi dot pj is mu bar squared delta ij minus 1/4 equal to lambda. But that's one choice. Doesn't need to be this. You can choose something else. So all these kind of ideas where you relate the full effective action with momenta that are some fixed scale, with being equal to, numerically equal to what happens at the tree level. These are called normalization conditions. So this is another way of thinking about renormalization rather than this one. So this one means we just subtract something divergent. But this one is another equivalent one. So meaning in particular that if I change subtraction scheme, if I go from one subtraction scheme to another one, then I also go from some normalization condition to a different one. All right. So So these are the two ways of thinking about normalization. About subtracting something infinite plus maybe something finite, or defining things at some scale to be equal to the tree-level stuff. Okay? And one more observation at the end of last lecture. I had said that this AK, there was this AK of lambda, BK of lambda, and CK of lambda, which were the coefficients of the divergences in m lambda and phi. So at order lambda k, sorry, at order 1 over epsilon to the k. Now, so I wrote it like this, but in principle, should have been also in terms of n over mu. So that's also, so that's a dimensionless parameter, lambda, but there's another dimensional parameter now, m over mu. M being the mass, and mu being this arbitrary scale mu. It's just that in the case of MS, in the minimal subtraction scheme, it just happened to be that it doesn't depend on m over mu. All right, let's move on to the normalization group equation. All right, so we've defined this minimal subtraction scheme, and there was this arbitrary scale mu, but then this arbitrary scale mu, it turns out that we can trade it. We can trade it. We can go from it to another scale, meaning the physical one. The physical scale mu bar. This physical scale mu bar, why do I say physical scale? Because here I am talking about the quantum effective action. That's something you can use it to define S matrices and so on, or calculations, or physical calculations, and momenta, the momentum scale here was mu bar. So this was something that is a physical scale. So while initially you had introduced a mu that was apparently out of the hat, you had to put in a mu, it turns out that you can trade this mu with a more physical mu bar. And then the dependence on this mu bar of the physical endpoint functions, the gamma n's, these are called the renormalization group equations. So let's restrict to phi 4 in 4 dimensions, since it's a very simple example to simple and physical example to analyze. And in this case, we've seen that the coupling constant is dimensionless in 4 dimensions. And we've seen that also in 4 dimensions, the superficial degree of the divergence was 4 minus E. 4 minus the number of external lines. So that means if I look for n.1 pi function, I will get 4 minus n. In which case I would get so if I restrict to a diagram that's finite, so now capital D is a diagram and it refers to a diagram that's finite, then this thing will depend only on momenta and on the mass, and it will depend through this superficial degree of divergence. So gamma n d at pi n. Right. However, now what's interesting is when I sum all the diagrams, and then some of them will be infinite, as we know, and then the parameters will be renormalized. So that means that here was also T. So that means that now I have to introduce, because it's renormalized, I have to introduce the scale mu, the arbitrary quantum scale mu. And then the endpoint function will depend on the momenta and the mass, but also on mu. And then again, the dependence will be via t minus n. Now, taking a derivative of that, specifically t dt, then of gamma n t pi t mi and t mu, then this would be 4 minus n times the same without t. Ti and mu. But then you see I have also T and mi, T multiplying mi, T multiplying mu. So in here I have ddt acting here, here and here. I can still act here, but then I can trade t ddt with the derivative with respect to m, and here with the derivative with respect to mu. So then I write t ddt partial gamma n on ppi, then plus m, plus the derivative with respect to m, so m dm, and plus m mu dd mu. And I can put also this term to the other side, so n minus 4, then gamma n, now tpi, so now I'm talking about the scaling with respect to physical momenta, pi, right? And then m and mu equal to 0. So that was my statement that I can trade the dependence on mu with a dependence on mu bar, right? So now I have a running that relates the two. So I relate this, which is basically the relation with respect to mu bar, with this, which is the dependence of mu. All right. And I can find one more equation, which is the following. The thing is that the bare effective action, gamma 0, so this is bare, so it does not depend on mu because that's the arbitrary quantum parameter. So I write that mu dd mu of gamma 0 n of pi m0 lambda 0 epsilon is 0. Well, kind of trivial in the sense that this does not depend on mu. But then I rewrite this in terms of gamma. This is gamma n of pi m lambda mu epsilon, and then with z to minus n over 2. So now it's non-trivial. And then we write the relations we wrote before, that this depends, so the polynomial lambda depends on the quantum parameters mu and epsilon, but also on the bare parameters lambda 0 and m0. And then that m, it's something that depends in perturbation theory. but then lambda depends on mu. So now, and then this also depends on epsilon, as usual. And that z depends again in perturbation theory through lambda of mu and epsilon. So then mu dd mu can be written as the partial derivative, but then there are implicit dependencies of mu in lambda. Sorry, d lambda d mu. And there is also a dependence on m. So now this object in here, I'll call the beta function. Well, let me write it on this other blackboard. So the beta function that depends on lambda and epsilon is this mu d lambda d mu at fixed m0, lambda 0 and epsilon, fixed bare parameters and fixed epsilon. So this is beta function. Then I have this object dimensionless, so the object that appears in here is mu dm d mu, but this has dimension, so I divide by m. So this is called the anomalous mass dimension. And then finally, this object in here was also depending, that phi was also depending on mu. So I define also mu over 2 z phi dz phi d mu. Define is this at gamma d of lambda epsilon, which is known as the anomalous field dimension. Alright, so these definitions seem kind of abstract, so let's see what that means. So obviously this thing can depend on perturbation theory and on epsilon, but let's assume that that they are constant, that the dependence is trivial, that they are actually constant. Then we will have what? So so this is the log mu, right? So here I also have the log mu, and also here the same thing. So we will have the fact that the derivative of lambda with respect to log mu is a constant cos delta, means that lambda is maybe lambda 0 plus beta log mu. And z in here, on the other hand, now here this is the log z. So this is now so whereas here I have just lambda, through this definition I have that log z is proportional to log mu, which means that z is a power of mu. Specifically, it means that this is a constant plus mu times 2 gamma d. That is what why I call this a field dimension. That's why I call this an anomalous field dimension. So this is what multiplies the field phi, and so the field phi so the field, the relation between phi and phi 0 was through z. So if z didn't have dimension, then these would have the same dimension. But now this adds an extra dimension to the field. So this is why this is called the anomalous field dimension. And similarly, I have that. So here I also have the log m the same way. So I have them. M is also some C tilde mu gamma m. Oh, and by the way, field, because the factor of 2 is because of the factor of square root. So I have that phi 0 was phi square root of z, right? So I have square root of this, so then I'll have mu to the power gamma d. All right. So with this definition, now let's substitute into the previous equation, into this one. So we had, this was the second equation. So the first equation we got was this one, and the second was this one, and now this is called beta, and this is called so divide by m times m, so it's m times gamma m, and then the derivative of this will give, so we'll get minus n over 2. With when I act with partial derivative on z, we'll get minus n over 2. And then, with respect to this, I get the same back the same z, then times 2 gamma d. So the 2 cancels, and finally, well, let me write it here. Yeah, I think I'll write it here. So then finally I get that mu d mu plus beta d lambda plus gamma n of lambda n ddn plus minus n gamma d times gamma n of pi lambda n mu equal to 0. Right? So, yeah. So this was the second derivative. So the first equation was this one. And then the second equation that we've obtained is this one. And now let's eliminate mu dd mu. Remember what I really want to do. So mu was an arbitrary scale, quantum scale that we introduced. But remember, I said we wanted to trade it for mu bar, or in other words, for the dependence on the momenta, on the scale of the momenta. So what I really want to do is to eliminate this mu dd mu in between this equation and this equation. So when I do that, I get that. All right. Let me see. So maybe, yeah, the way I wrote it, I substitute this with minus ddt. So minus t ddt. Then here I get a minus n ddn, but from here I had plus n ddn with a gamma n in front, so gamma plus gamma n of lambda minus 1 n ddn. Taking care of these things. Then I have plus n dd lambda minus n gamma d. So plus beta dd lambda minus gamma d minus n gamma d lambda. And then I have plus 4 minus n, so it's minus of this. Plus 4 minus n of the same gamma n t pi m mu and lambda, of course, equal to 0. All right, so this is called the renormalization group equation, RGE. So this is an equation that truly defines the dependence of things that you can measure, this 1 pi endpoint function, or in other words, the quantum effective action, the dependence on momenta, on momentum scale. So T is multiplies external momenta. So T dt refers to the dependence on the momentum scale, and that is defined through this object. So the mass defect, anomalous mass dimension, the beta function, and the anomalous field dimension. So these three coefficients define the RGE. All right. So I am absurdly late. Well, probably not being able to finish this lecture. Let's see how I'll do. All right, so now that I found this equation, let's find a solution. Right? So we find, so remember there's the dependence on lambda. There's dependence on lambda and the dependence on t, right? And then also dependence on m. So what I'm supposed to do is to solve lambda in terms of t and m in terms of t. So let's say lambda bar t d dt is beta of lambda bar of t. So we define these things, and t d dt m bar of t is m bar of gamma m lambda of t, lambda bar of t minus 1. So we define these objects with a boundary condition that lambda bar at t equal to 1 is lambda and m bar at t equal to 1 is m. Then the solution is lambda bar of lambda and t, and m bar is m bar on m lambda and t. Right? So these are through the boundary conditions. This depends also on lambda and m, and then this depends on this. So so we've defined some through this definition with this boundary condition, we define a solution for some lambda bar and some m bar. Now, to find the solution of the RG, I need to find the solution for gamma n, and the solution is written in terms of this lambda bar and m bar. Namely, gamma n of T pi lambda n epsilon mu, is equal to t to the 4 minus n. That's the thing that we expected. But then I have exponent of minus n integral from 1 to t ds over s gamma d of lambda bar of s gamma n of pi lambda mu, lambda bar t n bar t and mu. All right, so this is the solution. I mean, it's a bit complicated to get to it, to prove it, but you can check it. So reversely, now that you know that this is true, you just plug it into the renormalization group equation and find that you get this. Now, have we solved this? Well, of course not. We have not really solved it. This is a formal solution. Why is that? Because these objects that we define here, these objects that we define, the beta function, the beta function, the anomalous mass dimension, and the anomalous field dimension, these things are calculated only order by order in perturbation theory. And so, of course, you know, we can solve this at some level. So we can solve, let's say, for beta, gamma, and gamma n at one loop, let's say, and then plug into the renormalization group equation and find an RGE that corresponds to that calculation. So one loop. Now, note that the naive scaling was just with this factor without this exponent, and then in here just p and lambda and m, right? So this is more complicated than the normal the naive scaling of gamma n. What else? Well, let's note that if this is So let's say that m bar, if m bar is m over t to 1 minus gamma n. So if this is constant, then the solution would be m bar was m over t to 1 minus gamma n. If also lambda bar is approximately lambda, so from this equation, if beta equal to 0, lambda bar is approximately lambda. What else? And well, if gamma d is constant, then so if this is a constant as a function of s, then I integrate here. This is d log s. So the result will be just log t times gamma d. So this thing would be e to minus n gamma d log t. That is to say t to minus n gamma d. So an approximate solution then is for this thing to be equal to t to the 4 minus n 1 plus gamma d, gamma n of p lambda m over t 1 minus gamma m and mu. Right, so that's the sort of simplified solution to the RGV. All right. So we talked about the renormalization group equation, its formal solution, which you can make it precise by calculating these three parameters perturbatively, beta, gamma n, and gamma d. And we've seen that the simple solutions seem to be where the dependence of t is added gamma t in here, and where m is divided by t to 1 minus gamma m. Now, an important object in this analysis is the first one, the beta function, which defines the dependence of the coupling with t. And remember that t is really related to the physical scale mu. So let's talk about beta function and the running coupling constant. So to define the coupling constant, so we say that this, we have seen that this lambda depends on t, and that depends on mu, and another words of explaining it is with respect to dependence with respect to t, which is related to the physical scale. So the definition was beta of lambda is mu d mu lambda at fixed m0 epsilon. But from the renormalization group equation, we found that lambda depends through t, which is related to the physical scale. So that means that there is a truly dependence of the coupling to the momentum scale. So that means that this is something that you can actually measure experimentally. So people have calculated, in particular in QCD, so both calculated and extracted from experiments the dependence of the coupling constant on the momentum scale, or S, let's say, the momentum involved in the experiment. So that is why, in particular, when you consider when you collide particles at very high energies in QCD, the only thing you need to care about is one loop calculations, or maybe two loop. So the coupling constant is very weak, whereas we know that that nucleons, which are at zero momentum in some sense, have a very high scale. Now, it happens, so it's possible that lambda is approximately constant if, so near the point where beta is equal to 0. So if beta is equal to 0, then by definition does depend neither of t on mu. So it means that then so this would be called lambda f standing for fixed point. So near a fixed point f, the coupling constant lambda is 0, and the fixed point means that beta is equal to 0, independent of scale. Now, I was saying that for QCD, lambda for pi going to infinity goes to 0. This is known as asymptotic freedom. I don't know who coined this term, but certainly somewhat whimsy, that asymptotically, so at large momentum, we have freedom, it's uncoupled. Reversely, that means in QCD we also have that when pi goes to 0, then this is large, or I mean not necessarily going to infinity, but very large. So that is called infrared slavery. That's why I said whimsy, because freedom is the opposite of slavery here. So, now in QED, this is opposite. So lambda at pi goes to 0 is small. We know how small is approximately, I mean, lambda, the QED coupling to constant is 1 over, so alpha really, it's 1 over 137. But then also it happens that QED for some pi, some large pi, goes to infinity. But the weird thing is that actually pi is not infinite, but rather for some finite but very large p. So this is known as Landau pole. And we'll see how to calculate so if at 0 if at lambda equal to 0 I also have that beta is equal to 0, which is, well, not at all obvious, but it's supposed to be. So that means it's Taylor expandable. So this is what we mean. So this would mean that there is perturbation theory. And then, according to this definition, that if beta is equal to 0, then I have a fixed point where lambda is approximately constant. Then this is called the universal fixed point, or the Gaussian. Fixed point. Gaussian in that the path integral is Gaussian. It's quadratic around it. All right. Next, let's understand what kind of beta can we have? What possible behaviors can we have? So first, we note that the solution to, so if I said, well, I erased it, but we said ddt lambda bar of t was equal to beta of lambda bar of t. So the solution to this is that t is exponent of integral from lambda to lambda bar of d lambda prime over beta lambda prime. All right, so let me write here the possibilities for beta of lambda are the following. So the first one the first possibility is this one, the simplest one. Then the next possibility is that it grows, but then it goes through 0. And then here we find, so beta is 0 at some finite coupling, so there's a finite fixed point lambda f. That's number 2. Then the other 2 possibilities are basically mirror images of these. So where I have this is 3, and this, and the f is 4. Alright, so first, so in this case, if this goes to infinity, if this goes to infinity, then beta goes to infinity, and d lambda prime over something infinite means this is convergent. This is convergent. But then it means that if it is convergent, that means that there's a P0, which is this convergent thing, x integral from lambda to infinity of this thing, right? So what does that mean? That means, remember, T is what multiplies momenta. So T is basically the energy scale, dimensionless energy scale. So that means that for a finite energy scale, we have beta that goes to infinity. We have, lambda that goes to infinity. So that means that lambda goes to infinity at finite T0, meaning P scale. So this is the lambda of Paul. So this is the what QED looks like. So now if lambda bar goes to 0 and lambda also goes to 0, then this integral in here, so this is lambda and lambda prime, though these are both 0, and then this thing is approximately beta prime at 0 times lambda prime. But then this is d log lambda prime. So so this is in between two things that goes to 0. So this object t goes to 0. So this is IR fixed point, IR Gaussian. So this is IR Gaussian fixed point in this case, which is the behavior of QED. QED, as I said, has for t going to 0, for energies going to 0, has a fixed, has a lambda going to 0. All right. Also, we might notice that since this grows, so beta is positive, means that lambda increases when mu also increases. When mu increases, and also that lambda decreases when mu decreases. But so if I increase mu, that means no, okay, let me think of this one. So if mu decreases, then lambda also decreases. So you are driven towards the fixed point, which is lambda going to 0. This one, and this one I don't understand very well now. But the point is that this is stable now, stable fixed point. Now, in the case 2, I have in the case 2, I have also lambda, so we have lambda equal to 0 and lambda equal to lambda f. These are fixed points. Now in here, the derivative is negative. So beta is approximately beta prime lambda minus lambda f, because this thing is negative. So that means that in the exponent, from lambda to lambda bar going to lambda f, d lambda prime minus lambda f, I subtract this, and then here I have this beta prime, which is negative, and lambda minus lambda f. Alright, so this is the log lambda prime minus lambda f, but then this is something finite and negative. Oh yeah, sorry. Yes, I was getting confused. So this is in between lambda prime, lambda f and lambda. So this is then minus 1 over something times log of lambda f minus lambda f, so 0, minus divided by divided by lambda minus lambda f. Well, so I have, oh yeah, well, yeah, I have this 0 here, so otherwise I can rewrite this as plus 1 over something log lambda minus lambda f over 0, and the exponent of this is lambda minus lambda f divided by 0. Oh yeah, okay. So this goes to infinity. So this is lambda minus lambda f over 0, that goes to infinity. So that means that so means that t goes to infinity for lambda going to lambda f. So this is then a UV fixed point. In the UV at large t, that means large momenta, we are at a fixed point. And this is stable because if lambda is positive, then beta is negative. So sorry, if lambda is greater than lambda f, beta is negative. So we've driven to mu. So if lambda decreases, if it's smaller than lambda f, then mu will increase and we'll take it back to lambda f. So that means this is uv fixed point and it's stable. Then this is the same as this one, so no need to describe this. Now the case 3 is the mirror image of 1. So the case 3, we have that exponent integral from lambda bar goes to 0 to lambda d lambda prime over beta lambda prime, but now beta is negative, so minus beta prime lambda prime. So this, as I explained in here, this goes to infinity. So it means that when t goes to infinity at in uv, then lambda bar of t goes to 0. So this is Gaussian. UV fixed point. So this is the phenomenon that we called asymptotic freedom. So this is what happens for QCD. On the other hand, since beta, So if beta decreases faster than minus lambda, then what happens is we get a Landau pole. Because the exponent of lambda, for lambda going to infinity, d lambda prime over beta of lambda prime. So this increases faster than lambda prime. That means this integral is something like 1 over so this is from lambda. This is 1 over some power, so 1 over lambda bar to some power. And then exponent of this is some finite object. So at infinite coupling, we get infinite coupling for finite momentum. So that's what we call the Landau pole. And that's okay. So that's okay because we know that for QCD, the perturbation theory breaks down in the IR. And finally, for case 4, that's always the mirror image of 2. So again, there's a lambda f where beta can be expanded around it. But now this is positive. So this is but in this case we get that t which is exponent integral lambda going to lambda bar going to lambda f to lambda, then d lambda prime minus lambda f over some positive thing, and then lambda minus lambda f. Now this I get exponent of some positive thing times log 0, but log 0, so log 0 from this end, so this is d log d log lambda minus lambda f, but at lambda f this is 0, and the coefficient now is positive. This thing is now positive. So exponent of a positive thing times log 0, this goes to 0. This goes to 0. So this means now that this is in the IR. So this is an IR fixed point. And it's also stable. And then lambda bar going to 0 is in the UV, as in the previous case. All right, so these are the possible behaviors for the beta function. The first case is for QED with some Landau pole. Then the third thing is for QCD. And so this is Landau pole in the UV. This is Landau pole in the IR. And asymptotic freedom. And there's also these other possibilities. All right. Now there were a bunch of calculations, which I don't have the time to do them. Well, perhaps I'll do something quickly at the beginning of the following lecture, but that is everything for today. All right, thanks. Yeah.
You're done?
Yeah, no, let me just get out of this
Do you need
thing.
help?
Sorry?
Do you need help?
No, just getting out of Skype. I forgot how where it is because how do I get?
You're just here.
No. I'm getting out of the logging out because this is really. Yeah, in fact, Sayer. Yeah, thank you. Configure. No, of course not.
Okay.
Good. And and there's also